Good morning, FR 345. I'm here in a secret underground lair deep in the heart of ESF campus, broadcasting to you. There have been some threats. You've heard about the exam? Not really. I'm actually in the Soil Science Society of America meeting, and so you get to have me secondhand. And today we're going to talk a little bit about soil aeration and finish up erosion. But first, you've got to take a look at my comic. This will be a little one for all of you hunters out there, a little bit of appreciation. And so hopefully you're on the right end of that. Well, remember where we were. We left off last week talking about soil erosion. We were wrapping it up. We talked about its definitions and impacts. We then think about some models. We talked about the wet model, the universal soil loss equation, and the revised universal soil loss equation. Kind of got our thoughts around that and how to predict erosion. And we left water erosion, then talked about wind erosion, and we ended up on the mechanics. So just as we were leaving yesterday, we were talking about saltation and creep, and that's where we pick it up today. So the wind mechanics for wind erosion, and the third one was suspension. And suspension, unlike saltation, which was the major one, suspension is relatively minor, 15 to 40%. So that seems to be not very much movement. But yet, when you think about erosion and wind erosion, it's the thing that comes to mind, right? You think about these spectacular dust storms. And so with that, you see things like what we'll see in this slide. This is a picture postcard. Of course, it's a little earlier, back in the days of the windstorms and at the beginning of the Soil Conservation Service. But here we're looking at this typical dust storm, and this is one of the things that got people really worried about soil erosion. And again, it's the real spectacular thing that we see and think about, but it's not the majority of the problem. So now we think about what factors affecting wind erosion. Before we had the wet model, and we had the universal soil loss equation model for water erosion. And now we move into the factors of wind erosion. There's actually a wind erosion model, but we won't go through with that. We'll just kind of consider the factors and not consider the dynamics of that model. And first of all, the most obvious thing would be wind velocity. So how fast does the wind have to be to pick up some of these particles? And you're looking somewhere around 25 kilometers per hour, 15.5 miles per hour. Right? So that 25 kilometers per hour, that's kind of the key thing. And once the wind hits that velocity, then it's able to pick up these particles. And remember, we're talking about the fine sand and silt-sized particles. Okay? So we have wind velocity as being probably the first consideration. Next, we think about turbulence. So the wind, it's not a constant. There's a lot of turbulence, and the more turbulence, the greater the turbulence, the greater the probability of picking up particles. So you get these bursts of winds and increase in velocity. Some of these changes going from slow to fast. So more turbulence means a greater propensity to pick up particles. So the wind erosion gets worse. So we have, it's not just one solid speed or velocity. It's this combination. And then roughness. What about the surface? So some surfaces are very smooth, some are very rough. Right after you plow, things are very smooth. But normally the roughness is more the rule. So the more roughness, the greater the roughness of the surface, the better the soil's chance to resist some of this erosion. You have these little rifts and valleys. So a smooth surface, greater erosion. A rough surface reduces wind erosion. So we've got velocity, we have turbulence, and we have surface roughness. Kind of these are wind factors. Okay. So we move along and we get to soil. So now we've considered the wind, okay, and now we consider some of the soil properties. And there are a list of these, and they would make sense, intuitively they'd make sense. We think first about mechanical stability. So as in all things soil, aggregate stability is desirable, and it's desirable also from the point of erosion. More stable aggregates means a greater propensity to reduce the impacts of erosion, the particles hold together. And then there's something else in drier soils, crust. So when soils dry out, they tend to form a crust over the top. While this is bad for infiltration in drier lands, it has a positive advantage, and this reduces the propensity to pick up particles. This crusting is good from that respect. It's bad in terms of infiltration, but in terms of reducing the ability of the wind to pick up particles, that's a positive thing. And so then we think about the next part, and we think about the bulk density. And so as bulk density increases, soil becomes tighter, more compact, then the propensity for wind erosion decreases. So a low bulk density would result in a potentially much higher rate of wind erosion, all other things being equal. Okay? And we get down to particle size. Now, of course, particle size is pretty optimal, around 1/10 millimeter. So the real big sands, they tend not to blow until you get these really horrendous winds. But right around the 1/10 millimeter, so you're looking at the fine sand size, this is the kind of the optimal particle size. You get to this in the silt-sized particle. We've already talked about LUS, the silt-sized particles that are wind-blown parent material. In terms of wind erosion, it's that fine sand silt right around that particle size that gives that are most favorable for wind. First of all, they don't adhere to each other, they don't hold much moisture, and second of all, that very light weight and small size allows them to blow around. Okay? And then we kind of top that all off with soil moisture. So soil moisture is key. It's one of the big ways to control erosion. So when particles are moist, the particles tend to adhere a little bit. And excuse me, it's one of the more appropriate ways, one of the more important ways to control erosion. So here we had a list of factors related to wind, velocity, turbulence, and then we get down to the soil factors having to do with the particle size, the density, the degree of adhesion, and aggregation. And together these things give us the combined way to think about what's happening with wind erosion, what's susceptible, what's not. Okay. And throw on top of that vegetation. And of course, vegetation kind of holds particles together. The roots hold things together and it protects the surface. So increased vegetation reduces the problems or the propensity, the probability of wind erosion. So those are the issues. Those are the factors. And if we think about wind erosion, we think about it in those contexts. It's a good way to think about what's happening, also of how to prevent it. So that leads us to our next slide. Controlling wind erosion. There are the big three in terms of controlling erosion for wind. And the first one's soil moisture. So moist soils tend not to blow. So as soils dry out, they become very susceptible to wind erosion. Okay? The second part of that is tillage. Okay? So completely tilled soils. We talked about BMPs and minimal tillage and conservation tillage, and it folds into wind erosion. Okay? So as you till the soil, you remove vegetation and you expose the soil to drying, at least the surface. That creates or increases the probability of potential for wind erosion. So you can reduce that probability by kind of limiting tillage and not doing this complete moldboard plow, complete clean surface. And lastly, barriers. So this is the third way to control it. So normally we'd have barriers, and the idea with a barrier is to prevent or slow down the wind. And if you put a barrier, a row of trees, a row of plants, a snow fence, perpendicular to the wind, okay, this will reduce the propensity for wind erosion. Okay. So how does that happen? So I have a slide that kind of illustrates that, and this is from the book. So we look at this from page 784, and these are soils. These are organic soils. You can see they're beautiful dark soils, and you can guess which direction the wind is coming from. Okay, it's coming from the left. Okay, so these barriers perpendicular to the wind direction provide a way to slow down, stop the wind, reduce the velocity, and kind of eliminate the first factor in wind, velocity. So if you reduce the velocity, you reduce the propensity of the soil to erode. Here's another illustration, and this is, again, the same next page in the book. This shows what happens with wind velocity. This is in meters per second. Okay? And so here we're at about 12 meters per second, 9.5, and all of a sudden you hit the barrier, and there's a slight increase, okay, as the wind goes up and over the barrier, and then a marked decrease. And so with that marked decrease, all the particles that tend to be carried all of a sudden are dropped here. So that's why with a snow fence or any kind of wind barrier, when you look at where the material builds up, it's always on the leeward side, because that's just beyond the leeward side where the wind velocity drops and the particles fall out. And the effect of this is about 20 times the height of the barrier. Here's 20 times the tree height. And so this is a pretty good effect. So if you're trying to space or manage for wind erosion, and we go back to our last slide, so if I can do that. You see your spacing depends on the height. So the higher these are, the wider you can space them. And so part of your management for controlling with barriers is looking at the height. And this is a pretty nice distribution. Okay, we go back to this field, and here you can see that some of this dark, so these are organic soils, but some of this dark is due to moisture. So part of the control here, and this is particularly important for organic soils, has to do with moisture. Moist soils won't blow, and these low organic soils, these low bulk density soils, keep them wet, and have barriers. And so here you're looking at 2 of those 3 control devices. What you don't see here is vegetation. It's just before planting. So the vegetation will top it out, and then all 3 of those prevention methods would be in place. Okay. So how do we look in terms of the big picture for the U.S.? Here is the data, some data summarized in the text showing the estimated soil loss from '82 to 2003. And this plots the soil erosion rate, megagrams per hectare, a figure you're used to seeing, 10 to the 6 grams per hectare, this 10,000 meters squared per year. So this is annual erosion rates. And we go from 1977 up to 2008, 2003, and voila, you see, this is good news. There's been a successive reduction in the combination of wind and water erosion. Of course, we said water erosion was mostly by sheet and rill. Okay? So this would suggest that all of our efforts, the USDA efforts and national efforts to reduce erosion and to apply best management practices, keep the soil on the site, they are effective. And these data are pretty encouraging. It shows that our efforts, while they're not 100% great, okay, our efforts are paying off, and so we continue to monitor and we continue to look for ways to reduce erosion. That's a very comforting slide. There's another interesting study. So this was in Science, and it was almost a decade ago now, a little over a decade ago. And so this was by Trimble. So Trimble was a pretty famous hydrologist with the U.S. Forest Service. And he had this article. This was partly in response to some of Pimentel's big in-your-face numbers about the impacts of erosion. And this one was to look at erosion in a specific site. So this is the Coon Creek Basin. This is in the driftless area of Wisconsin. It's been ag for a long time, since the turn of the century. And this is kind of neat because at this area they actually measured losses. So these measurements came from cross-sections. There are 150 of them, cross-sections that were studied over the period from 1938 up until present time. Okay? So in 1938 they put in these cross-sections and they actually measure the soil, okay, and the soil as it accrues, and go back in '92 and we measure that again. So here you're looking at something that was buried. You see the layers of soil. So these are actual measurements of soil accretion in this basin over almost 100 different points. So again, this is measured, not modeled. That's the key thing about this study. So he summarizes that, and if you look at the period 1853 to 1938, and this is when all the land clearing was going on and agriculture was pretty big, and at this point in time, there's very little in the way of any kind of practice to minimize erosion. They're very exploitative, just plowing, moldboard plow, clear everything off, and just farm. And it was a period of time where the U.S. and in general we were not sensitive to soil erosion losses. And there was just kind of no attention paid to it. It was just the idea then, or the goal was to get the crops in and just plant as much as possible. And so we look at some of the erosion. So this is showing the erosion, okay? And these are in average 10 to the 3 megagrams per year. So that's 71,000 megagrams per year. And it's showing where the soil is going based on the aggregation of the data, those cross sections. And you look at the end. So sediment yield to the Mississippi River, okay, was about 38,000 megagrams per year, okay? And what's really interesting is where this is all going. So here's the rate of erosion, 326 from sheet and rill erosion, okay, 326 times 10 to the third megagrams, and about 73 going to gullies. And again, this also makes the point we made earlier, that the majority of the problem of erosion comes from sheet and rill. And we said gullies, while they're spectacular, they're kind of neat looking, but it's not the major part of the problem. The major part of the problem for soil erosion loss, sheet and rill erosion. And this graph illustrates that nicely. So look at this, all this deposit. So most of that material is being deposited into the lower valley. So it moves down to the lower valley. Some of it ends up in the upper valley and the tributaries. So, but very little of it makes its way to the Mississippi. The yield is relatively small relative to all the material that's moving. So this is all the soil that's moving and moving into sinks. So these sinks in the lower valley, the upper valley, the tributaries, these are the sinks. All that soil is moving off the farm fields. Okay? Now the next good piece of news, in 1938 to 75, and this is the beginning of environmental awareness and the beginning of farm plans and the beginning of efforts to control erosion. And look at the reduction. We've gone from 326 upland sheet and rill erosion down to 114, almost a third. Okay? And then a significant 15–20% reduction due to gullies. Okay? And note this here, the yield to the Mississippi River is about the same. Okay? It's not very much difference. It's a little smaller. But what the big difference is in the deposition of material, all that material moving has been slowed. So now in the upper valleys, instead of putting in 71,000 megagrams per year, now it's 27 in this period on the average. Okay? In the lower valleys, almost half. So the amount of material moving is smaller. The sinks are still aggrading. Okay? There's still sediment flowing into these. Okay? So that's 38 to 75. And then we go to the most recent period, 75, 76 to 93. And again, a tremendous reduction. We're down to 76. Okay? The deposits in the tributaries, the upper main valley and lower main valley, tremendously reduced. The yield to the Mississippi, still not very much different, about 37. But the big difference is in the amount accretion, the amount of soil moving around and ending up in lower parts of the valley. So here's a picture of that in a cross section to see what that means for depth. Okay? So here we go from the 51 years from 1853 to 1904. Okay? Here's the beginning of clearing. And we go 1904 to 1930, and we look at that. From 26 years, there was more than a meter of sediment deposited. Okay? So this is that period of very intense agriculture with minimal impacts, minimal laws, minimal BMPs, mostly just mold board plowing, clear cropping, and just no worry of erosion. Okay? You get to 1930, go up to 1938, in that period of 8 years, again, almost another meter of sediment. Now we come to the period 1938 to 76. Here's the beginning of environmental concern, the beginning of the EPA, the beginning of some of these farm programs in response to all this erosion. All that spectacular wind erosion from around the turn of the century got people's attention. And again, this moved the country to very explicitly to try to reserve and preserve soil. And we look at the impacts of that. So you look at that graph, and in that 38 years, now there's well under a meter, about 30 centimeters of soil deposited. Then we get into the most recent 17, and it's cut down again. So this is extremely important in terms, this is showing us the tremendous impact that, at least in measured impact in one particular valley, of the improvements due to BMPs and the attention due to erosion control. So that should be very encouraging for anyone in a federal agency that's had involvement in that. It's a pretty amazing testament to the positive impacts of all that good work. So I can summarize that for you in numbers, just to give you an appreciation if the graph isn't enough. Here's that 53 to 58. The sediment storage was 405,000 megagrams. From 38 to 75, it went down by half. Okay? And then 78 to 93 went down again by an order of magnitude. Okay? So the emphasis 78 to 1993, to put that in perspective, it's 6% of the 1920 to 1930 period. And the final with that, I want to tell you that we've talked about flux and yield. Sediment flux, all that movement, does not equal yield. Okay? Sediment yield is referring to the amount delivered to the water body, in this case the Mississippi. So, and that didn't change very much, 36, 38, 32. That was very little annual change. The big change is in the amount of material moving. Okay? So how does that look visually? Interesting enough, Trimble had some pictures, and of course the Forest Service and the federal agencies are famous for taking pictures of their sites and kind of documenting things visually. So here's a picture of that area in the 30s. Okay? And here it is in modern times. So look at the difference. Okay? Oops, I keep doing that. Okay, I'll have to excuse me, I've just got to get to the... I'm on a different computer. Let me get back to where I need to be. There. So we look at that difference. So back in the late 30s, you see a lot of erosion. You see no vegetation. The cows, the animals have access to all this stream. Nothing's fenced off, and it's pretty much eroded, gravel exposed, and not much in the way of vegetation. So a very different picture. We bring that picture up to the 1990s, and it's all well vegetated. There are buffer zones. The cattle are excluded, all these BMPs that keep the cattle out of the stream. It keeps all this erosion. So all of those things, all those BMPs collectively have resulted in a tremendous improvement in water quality. So we have a lot to thank for the EPA for that and the federal agencies that are responsible for implementing these programs. Okay. Again, it's a marvelous testament to the success of erosion control and management and still maintaining agricultural productivity. Okay. So we've talked about erosion, we've talked about wind erosion, we've talked about water erosion, and now we come up to forest lands. And so forest lands are kind of the benchmark. So we talked, originally when we talked about erosion, we talked about accelerated versus natural. Okay. And accelerated erosion, everything due to the impacts of man. And then geologic erosion, natural rates. So we kind of use forests as the benchmark. We equate that with natural rates of erosion. And here's why. The overland flow in a forest is practically nil. So while water moves through the forest, moves through the profile, water hits the forest canopy. Okay? It's reduced in terms of its impact. Then it's slowed down. Then it hits the forest floor. Again, it's distributed evenly. And once it hits the forest floor, it infiltrates. Okay? So that infiltration moves water through. Then it starts to move through that very large system of biotic megapores and macropores that we talked about. So there's no overland flow. All this material is moving through the soil, through the system, moving laterally, but no overland flow. So no overland flow, we're eliminating the problems of accelerated erosion. What happens when you compress that soil, or you strip the soil of the forest floor, or you drive over it, you end up with an impermeable surface, and this starts to change the dynamics. And when those dynamics change, then we have erosion. And to control that, we have a series of BMPs that we talked about. We have that whole booklet of forestry BMPs that describes how to minimize those impacts, how to distribute and plan, and then how to reduce this impermeable surface. So all of those contribute to this tremendous reduction in erosion. And those are important in forest lands because forest lands are the source pretty much of all our drinking water. One topic I wanted to touch upon was forest roads, just to think about. So you think about a road's an impermeable surface. And this is kind of my cartoon showing the organic horizon, the soilum, the B horizons, and then the parent material. Okay? And so we think about what a road looks like in this situation. The road in the old days, a bulldozer would come along and just scoop and plow and push down to the impermeable surface, maybe basal till or hard pan or fragipan. And so in the old days, the bulldozer would just come and you'd be pushing right towards you and you'd see this like this. So essentially you're creating a ditch. This process creates a ditch. It's a pretty easy way to make a road, just drive a bulldozer. Okay, so you'll agree that's a ditch. Okay. Now how should a road be made? A road should be an elevated surface. Okay? So modern roads are made as elevated surface and material is piled up. Okay? So what happens with the previous situation? Okay. This is what that looks like. You have this is an old road. So there are thousands and thousands of miles of roads such as this in woodlands across the U.S. Okay? And you can try to get a picture of this, but this is a ditch. Right? So a bulldozer many years ago, 50 years ago, came and pushed all this out of the material. And you can see, so the sides are elevated, and you essentially have a ditch. So below here you have hard surface, hard pan. And if you have a ditch and the surfaces go up to the right and up to the left, water flows where? Water flows at you. Okay, you can't get water off the surface. It has to flow down the compacted surface. This results in a tremendous amount of erosion. There's no way the water can run up over hill. Okay? And so this is the basic problem with the old way of road construction. So this is the problem with this. You have a ditch. There's no place for water to go. Water has to flow down here. It just has to flow. It can't flow over here. Now, the proper way to construct a road, and we've come to appreciate this, something called the turnpike method, okay, is now to elevate the surface. So instead of digging and just pushing, now the idea is to excavate around the sides, dig ditches, and apply that material to the surface. So now we're building an elevated surface. So here's a ditch. This represents a ditch. Excavator comes along and piles stuff on top. Here's a picture of that process in place. This is a single grip harvester with just enough width to have the footprint for the road and enough for drainage. Okay. And the excavator comes along the sides, and the excavator pulls basal till from the ditches and piles it on top. So this is what it looks like at the end. Now, instead of a surface where the water has to go up, the water drains off the surface and goes down. Okay? So this is an elevated surface. It's slightly crowned, as we talked about, crowned to eliminate the water off the surface so that we don't concentrate water and flow down this way. Water flows off to the ditches to the side, to the left and right. These are the drainage ditches. Water is delivered down gradient, and we have a whole bunch of BMPs. We have cross drains as needed. Water is shunted off to filter strips, and water goes off. And all this ditch water is isolated from the drainage systems. These drainage systems water all isolated from the water system of fresh water, creeks and streams and so forth. And so this is the way a road should be. And this road is ready to drive on 3 months after it's built. Yeah. Okay, so that's pretty much ends up erosion for us. Okay, so we started out with water erosion, we went to wind erosion, and we talked a little bit about BMPs. Last week in the field, we looked at some of those BMPs. We looked at the things around Heiberg Forest. We saw some water bars. We saw some interesting ways to construct roads. We saw problems and we saw solutions. So all that kind of ties together in that field lab. And so that's pretty much the end of erosion, and it sets us up for the next topic. And so now we go on to talk about aeration and temperature. And this is a good follow-up as we finish up water, because as water moves out of the soil, we have airspace, and now we're talking about the ability or the capacity of the soil to exchange air with the atmosphere. And that brings us to the topic of aeration, and that leads us next to the topic of temperature. So what do we first think about in aeration? We probably think about the atmosphere. And so let's compare its systems in the soil, its concentrations of various gases with concentrations in the atmosphere. And so this next slide does that. Here we are, soil air versus the atmosphere. We have 3 main gases: nitrogen, oxygen, and carbon dioxide. There are many others, but nitrogen is about 78% of the atmosphere. It's this inert gas. That's just this triple bond. It makes it very hard to break down. We'll talk later about how to break that down. But for now, it's inert, and it's almost filler. Okay? And then oxygen. The oxygen in the atmosphere is about 21%, or 21 liters per 100 liters, the partial pressure of oxygen. And currently, carbon dioxide at 0.039%, or 390 ppm. So that's what the atmosphere looks like. Let's contrast that to the soil air. And again, these numbers are in percent. Okay? So roughly, nitrogen in the soil atmosphere is about the same. Okay? It's a relatively inert gas, and not much is changing. In general, in the soil, the concentration of O2 is lower. Okay, and how much lower we'll discuss as we go on with this, but definitely lower than the atmosphere. And then the carbon dioxide concentration in the soil tends to be higher than the atmosphere. And again, so lower, higher, by how much, that's the subject of the next bit that we'll talk about, soil aeration. So this is our benchmark: 78, 21% oxygen, 390 parts per million, or 0.039% CO2. That's our benchmark. And we'll evaluate the soil air, or the soil atmosphere, relative to that. There are other gases. There are methane and hydrogen sulfide, and so there are a whole bunch of other gases. Okay? And so those, while some of those are important, some of these are greenhouse gases, we'll focus for the most part on carbon dioxide and oxygen. And we will make some mention of some of these smaller trace gases that are because of the problems that can occur. So let's think about a well-aerated soil. Okay? So when we talk about a well-aerated soil, this is what we're talking about. We're talking about capacity for gas exchange, right? And so we need a definition. And so that we're all on the same page, we'll talk about a well-aerated soil in terms of gas exchange sufficiently rapid for 2 things to happen. Okay? And the first thing is that there's replenishment of oxygen. So here we are in the soil, we have to replenish oxygen. Why? There are a lot of activity in the soil, a lot of organisms. There are all kinds of aerobic organisms, and all of them need oxygen. And unless you keep replenishing that oxygen, their metabolic activity tends to slow down. Okay, so at the same time, all those aerobic organisms are respiring, And in respiration, they produce carbon dioxide. So in order to have these things move on, we'll talk about a well-aerated soil as being continually replenishing oxygen and continually removing or preventing the buildup of CO2. So that's our definition, and that's one you'll want to store in your memory banks. You'll probably be telling me about this in the next exam, and I know you'll be telling me about this in the final exam. And if you don't tell me about this in the next exam, your grade will be sufficiently low that you'll wish you had told me about it. So this is the time to kind of commit it to memory. So what controls availability of oxygen? So now we think about how do we get to an aerated condition, and we start to think about the constraints on oxygen and CO2 production. And so we'll review those. So the first thing is macroporosity. Okay? So soil macroporosity. And remember, large pores don't hold water against gravity. And we've been stressing that. So we've been talking about that in terms of water, and now we're going to look at the flip side of that. We're going to look at aeration, the ability to transfer gases. And so macroporosity is kind of a desirable thing because if pore doesn't hold water, it can hold gas. And this depends on two things, the texture and the structure. Right? And we've talked about that. We've talked about texture impacts and large particles and small particles, and sands tend to be large particles and clays small particles. Then we talked about structure, the aggregation of primary particles into secondary units, and how those modify the effects of texture. We talked about how that increases or improves macroporosity, that those well-developed, stable aggregates are very desirable. And they're desirable for all these reasons. And so now we think about it in terms of how we transfer oxygen and carbon dioxide into and out of the soil. And soil macroporosity has got to be number one. So the second thing is water content. Okay? So water is either occupying pores or air is occupying pores. Okay? And so we think about the air-filled porosity. So in bulk density, we introduce this concept of total pore space, okay, in soil physical properties. And now we're thinking about how much of that pore space is air-filled. Okay? Because again, the soil either has air in it or it has water in it. And so air-filled porosity is another way to think about this. Okay? So we have macroporosity, soil water content, and then we have consumption. And pretty much we're talking about biological activity. So roots aspire. Roots aren't the only organisms in the soil. There's a whole host of other organisms. And so we have both autotrophic respiration due to roots and heterotrophic, all the organisms. And the combination of this leads to a production of CO2 and the consumption of O2. Okay? So the biological rates kind of affect this. So these are the factors: macroporosity, moisture content, and O2 consumption. And these are going to lay the constraints that are going to define for us the sideboards for soil aeration. Let's think about gas exchange. Okay, so we've talked about these static things. Now let's think about what's going on. So there's two ways to move gas around in the soil: mass flow, and by mass flow, think about wind or changes in atmospheric barometric pressure, or diffusion. And so you see the big one here is diffusion. That is the primary way that gas is exchanged between the soil and the atmosphere. And again, not mass flow, but diffusion. So I guess we need to define diffusion. Okay? So diffusion is the movement of molecules to equilibrate a concentration across the gradient. So whenever there is an inequilibrium, there is always movement, and natural systems tend toward equilibrium. So this is showing the cartoon of the atmosphere and the soil, this white line here being the soil, and it's showing the concentration of oxygen, the partial pressure. You see there's a lot more oxygen in the atmosphere than there is in the soil. Okay? And this is just relative numbers. By the same token, there's a lot more CO2 in the soil, so all these little light browns, compared to the atmosphere. So there's a gradient, okay? And this gradient is going to change or changes, and diffusion is the mechanism that's responsible for this. So this kind of cartoon is kind of consistent with our earlier message that the concentration of oxygen in the atmosphere, 21%, is higher than in the soil, and the concentration of CO2 in the soil is less than the 0.039%, or 300 parts per million. And this kind of is an illustration of that. It's a visual illustration that holds up to that prior generalization. Okay, so the concentration of CO2 is higher down here, and so it tends to move from high concentration to low concentration. Just like water, things move from high to low. The same is true of gases, the high concentration to the low concentration. So the tendency is for the material, the CO2, to diffuse out of the soil into the atmosphere against this gradient. And this attempts to approach equilibrium. So at the same time, the concentration of oxygen molecules higher in the atmosphere, and by diffusion, they tend to move inwards, so they diffuse into the soil. So oxygen diffuses in, carbon dioxide diffuses out. Oxygen in, carbon dioxide out. Again, this is a response in concentration to a gradient. Diffusion. Here's the kicker. This process, this exchange, response to a gradient, diffusion, it's 10,000 times greater in air-filled compared to water-filled pore. So what does this mean? And effectively, if your pores are filled with water, there's no diffusion of oxygen and CO2. Okay? So this tells us that air-filled pore space is important, okay? And that air-filled pore space is related, for the most part, to macropore space. Okay? And the micropore is empty as more and more potential as those plant roots exert more and more suction to move it out. But basically, we're talking about macroporosity. Okay? And so hence we go back to our systems, this macroporosity, air-filled pore space, and biochemical reactions. And kind of this lays in there very nicely. And so essentially, air-filled pore space is needed for diffusion to occur. So let's assess it. Okay, so we've defined it, we've compared it to the atmosphere, we have an idea of the sideboards. Okay. Let's assess soil aeration. How do we do it? So the first way, and there are several ways, now we're going to quantify it. And again, in an exam I could ask you if some of these numbers and say, do I have a well-aerated system or do I have a poorly aerated system? So first we'll talk about the content of O2 and other gases. And we'll start out with oxygen. So generally, most upland plants require 10% oxygen. Okay? That's kind of, so you get below 10% oxygen in the soil atmosphere, and it's not very good, not very favorable. So this is an important number. This 10% oxygen is a concentration. Once you drop below that in the soil, you start to reduce the activity of aerobic organisms. Okay, so 10%, or that's expressed here, 0.1 liter of oxygen per liter of volume of soil. Okay, so 10% O2. Okay, so another way to think about this is in CO2, because CO2 is the production of respiration, and carbon dioxide, well, you know, too much carbon dioxide is not a good thing. So you remember the movie, one of those movies with Tom Cruise, The Right Stuff, I think it was, and so they're all furiously working in a space capsule because the CO2 concentration is starting to climb above 10%. They're getting kind of groggy, and they successfully make some kind of scrubber, and the movie continues, and the Apollo film goes on. Okay? Well, it's the same with plants. Okay? So this CO2, once that becomes greater in 10% concentration, or 0.1 liter per liter of soil, once that exceeds that, that becomes toxic. Okay? So it's 10% oxygen is needed, at least. Exceeding 10% CO2 is deadly. Okay? And so these, again, are the sideboards, just thinking about concentration. So a well-aerated system has to be above 10% O2, has to be under 10% CO2. Fairly straightforward. That's one way to assess it. How do we do it? Well, you can actually put probes in. We can take soil samples, atmosphere out, and measure the concentration of these two gases. I actually had a study, a project many years ago at University of Vermont where we did that. We compacted the soil. We'd go and extract syringe fills of soil atmosphere, bring that back and run it through the GC and get the CO2. GC, for those of you non-chemically thinking, gas chromatograph. Gas chromatograph, little tidbit. Okay. So we've talked about soil concentrations of oxygen and CO2. one way to do it, so we can quantify that. Greater than 10% CO2, bad. Less than 10% O2, bad. Okay, another way is simply with air-filled soil porosity. So if we look at the total pore space, and if less than 20% of that is air-filled, okay, that inhibits plant growth. Okay? So less than 20% of total pore space inhibits plant growth. Let's take that one step further. Consider that total pore space ideally is about half the soil volume. So if we say that's half the soil volume, we can compute that just to soil volume, or less than 10% of soil volume. Okay? So if we get below less than 20% of total pore space that's air-filled, or below 10% of the soil volume, this inhibits plant growth. Okay? So that's number two. So I've given you some figures for what's well aerated and what's poorly aerated based on the oxygen content and the CO2 content. Okay? And now I've given you some figures based on aerated or not aerated, based simply on air-filled total pore space or soil volume. Okay? Those are two. So let's go with a third way. So a third way to assess soil aeration is something called the oxygen diffusion rate, the ODR, oxygen diffusion rate. Again, it's another quantity. And this key value is about 0.3 of a microgram per centimeter squared per minute. Okay, so this is an important cutoff. 0.3 microgram per centimeter squared per minute. Okay, you start to dip below that number, and top growth, the above ground growth of the plant, is dropping off rather markedly. Okay, so this is a diffusion rate. It's the amount, micrograms, per unit area, in this case a centimeter squared per unit time. It's a rate, amount per unit area per unit time. Okay, so the number is pretty close to that for root growth. Okay, so 0.2 micrograms per centimeter squared per minute. So this 0.2 to 0.3 range, this is kind of not very good news for aerobic organisms, and so this is the cutoff. So we go from well aerated to poorly aerated, and this is our cutoff. So we add this to total porosity, macroporosity, air-filled porosity. We add this to our idea of concentrations of oxygen, concentrations of CO2, and we have now three quantitative ways to assess soil aeration. It's either good or bad, and these are the cutoffs. So I could ask you in an exam to tell me if I had a certain oxygen diffusion rate of, say, 0.7 or 0.8, would I have a well-drained soil? I might ask you if I had 35% oxygen, would I have a well-drained soil? I'd ask you about aeration. And so you could answer those kinds of questions based on these numbers. Okay? So there are links, quantitative links to these concepts of what is a well-aerated soil versus what is not a well-aerated soil, or what's a poorly aerated soil. Again, you're going to have to make this link, so these numbers are useful reference points. And again, the next exam, like all things, I'll ask you in some way, shape, or form, should I have enough time and space on the exam about these kinds of issues. So put a little star there, it's important. Not that all this other stuff is not important. Okay. So here's an illustration of that. Okay. And how do we measure it? We measure it with a platinum surface, and we can look at the change in voltage. And essentially, we have oxygen diffusing hitting this platinum surface, and the difference in voltage across this can give us is directly responds or directly related to the diffusion rate. And here's the illustration of it. It measures the rate of movement of oxygen through this system till it hits this surface. Yeah. So that's pretty cool. It's kind of tricky. Doing this in the field is tricky, and all these things, these measurements in the field are kind of challenging, shall we say. So here's some data to support it. So I told you this number of minus 2.2 to 0.3 micrograms per centimeter squared per minute. So here's some data. So these data actually come from a colleague of mine, a student of Larry Morris's down at Georgia, Scott Torianos. He's now I think he's a professor somewhere, but this is part of his master's thesis. And this shows the percent response of various things, cotton plants and root biomass, to this oxygen diffusion rate. So this was a kind of a greenhouse study where they imposed certain conditions and then measured both. They looked at the response of plants in terms of biomass and the response of plants in terms of germination. And here we have the logarithmic scale, 10, 100, 1,000. This is grams times 10 to the minus eighth, right? So we divide by 100, and we get the micrograms, okay, in tenths. So no, here's loblolly pine. So these data here are for loblolly pine seedling emergence. These little dots here, these orange dots, Scotty measured the seedling emergence and recorded that relative to the oxygen diffusion rate. Okay? So somewhere around 20 grams 10 to the minus 8 centimeters squared, or 0.2 micrograms. Okay? It's pretty consistent. That somewhere around 20, that's stopped, and there was a linear increase with increasing oxygen diffusion rate in terms of loblolly pine seedling emergence. Okay, so it's a nice illustration of that concept. Okay, here's the data for cotton roots. So cotton roots, this was measured in biomass of cotton roots. Okay, two very different systems, right? Loblolly pine, a tree, cotton, a plant, and the same kind of slope of that relationship. If you measure the biomass, the improvement in terms of root biomass was linearly related to this oxygen diffusion rate. And again, around 0.2 to 0.3, or 20 to 30, it pretty much goes down to zero, the biological activity. And this is a very nice data set that kind of supports that. And I use it because Scott and Larry are good friends, and they sent me this shot from Scotty's thesis from several years ago. But again, I could have dug up any number of studies, and most of these studies show around 0.2, 0.3 micrograms per centimeter squared per minute. That's where the going gets tough, and the tough don't get going. Okay, so that's our third way. So we've gone from concentrations of gases, we've gone into macroporosity of air-filled pore space, and we've gone into oxygen diffusion rate. And so there's another number, there's another cutoff, something called the redox potential. And this is measured by a change in voltage. EH is the redox potential. So the definition here, redox potential, exactly what it is, we're talking about the tendency of a system to reduce or oxidize. And remember what reduction is. A system reduction is the gain of electrons. Oxidation is the loss of electrons. And we can measure that as a potential or a change in voltage. And oxygen accepts electrons, right? So oxygen itself is reduced. Oxygen is an oxidizing agent. When it gets the electrons, it is reduced. Okay? Whatever is playing around with oxygen in there, usually it's iron, that is oxidized. Offload the electrons onto oxygen. Oxygen is reduced, and the other substance is oxidized. Clear? Let's use it. Excuse me. Let's show that with an example. So O2 is absent. Okay, so we've talked about this. This is anaerobic conditions. We talked about glaciation, reduction of iron. So when there's no oxygen, there's something else. So this is anaerobic, right? Anaerobic, no oxygen. Other substances accept electrons. Okay? Biological activity slows down. It slows down tremendously. It doesn't stop. There's still anaerobic respiration, and so respiration involves electron generation and transfer. So what's happening? Where do those electrons come from? So glucose, a simple sugar, breaks down to pyruvic acid and produces electrons. Okay? So you know the rest of the story. You probably, if you take biochemistry, you'll follow this pathway all the way down to the end. But for now, this little piece shows that when you take glucose and convert it to pyruvic acid, you generate electrons. So we're starting to respire. I see with this chemical equation, and this is respiration. We are starting to respire, but some of you are getting nervous and starting to perspire. But not to worry. Just the point is we are generating electrons from respiration. Well, here's a shot that shows how EH, or the tendency of a system to oxidize or reduce, what happens after saturation. So you saturate a soil. Okay? And a variety of things. So this is 0.2 plus 0.4 plus 0.6, going down to negative numbers. There's EH. And these are typical numbers. Okay? These are volts. These are volts. And days after saturation. And on this axis, we're looking at dissolved oxygen, milligrams per liter. Okay? And we're also looking at pH. So we got a lot of things going on here. So let's look at EH. Okay? Just after you saturate the soil and all the organisms are going, eventually, it's very soon after saturation that the oxygen is depleted. Okay? So let's travel with oxygen. Here's DO, not the daily orange, but dissolved oxygen. And so we're up here and we're on about 6 milligrams per liter, right over here, 6 milligrams per liter. And all of a sudden, within a day, that plummets down to less than 2 milligrams per liter. Okay? And all that oxygen is used up, and now it flattens out. Okay? And as we continue on, it's just depleted further and further. We're getting close to zero. So the oxygen depletion is very rapid. No dissolved oxygen. All the oxygen in that's used up and flattens out and just stays precipitously low. And this is way below the level for aerobic activity. Okay? So the EH, the system tendency to oxidize or reduce, measured in volts, that drops precipitously too. So we go from 0.6, and then all of a sudden as that oxygen is depleted, we go down here to 0, we cross 0, and we're in negative numbers. We're in minus 0.2, minus 0.3. Okay? So here we are in the EH. And that's pretty, minus 0.2 is very low. Okay? So what's happening with pH? After saturation, the pH is going up. Okay? pH is going up. And this is pretty typical. And what's happened with oxidation reduction? So right here, as soon as all that happens, we're all being reduced. Everything is reduced. Okay. Let's look at the EH for a peat bog. Okay. And let's relate that to oxygen diffusion rate. So here we have very low EH. This is millivolts. Okay, so milli, 10 to the minus 3. Okay. So 100 millivolts is how many volts? 100 over 1,000, 0.1. 300 millivolts, 0.3 volts. So whether we're in millivolts or volts, we're still thinking the same direction. These are the same magnitude of numbers. Okay? And minus 100 is minus 0.1 volts. Okay? So we look at the plot. So if you plot EH in millivolts, by the oxygen diffusion rate, as you increase the EH, you increase the oxygen diffusion rate. So what's that point of oxygen diffusion rate? Micrograms per centimeter squared per minute. What's the point we said was limiting and started to result in top growth ceasing? 0.3. Okay, so right about here. So our EH, right around 250, 200 to 250, the 0.2 to 0.3 range. So this is the cutoff. So here's the cutoff for oxygen diffusion rate going from plant growth starting to cease. Okay? And once you get above that, we get this rapid increase with this rapid relative increase with EH. So those two numbers are telling us the same thing, just different magnitude. So what's going on? Here is iron plus 2 with a little bit of water. Okay? So iron plus 2 to iron plus 3, that is a loss of electrons. This is the oxidation of iron. Okay? Where do those electrons go? Ah, the mystery. If oxygen is present, the electrons go to oxygen, and oxygen is then reduced to water. Okay? That's the oxidation. Oxygen got the electrons, oxygen is reduced. So let's add those all together. Here is the oxidation of iron. Here's oxygen accepting the electrons. And when we write that equation, you'll see this. We have FeO plus half O2 goes to FeOOH. We're going from plus 2 to plus 3. This is what we showed in the previous, when we talked about oxidation reduction. This is what we showed. This explicitly shows you where the electrons are going. Whoa, chemistry, blowing your mind. Okay, so we'll take a step back and we'll relax for a minute and think about what we've covered. We started out with wrapping up erosion. We went into the wonderful topic of aeration, We talked about what aeration was. We defined it. We looked at some sideboards of what controls aeration. And finally, we had a way to quantitatively assess it. Gave you 4 or 5 different numbers of how to assess it. And then we moved on to thinking about exactly what's going on. And we ended up with this idea of EH, the system tending to oxidize or reduce. And we showed that electrons are produced by biological activity. Those electrons have to go somewhere. And oxygen in an aerobic system gets the electrons. And so tomorrow's lecture, or actually Wednesday's lecture, we'll discuss on other things that get those electrons, and we'll pick it up. So with that, I'm going to cut off now. Your heads are probably spinning. But be aware that this is a taped lecture, so you can, if you miss some of it or are slightly confused, you can replay it again and become even more confused. So I'll see you next week, and don't forget to show up because this gets even more interesting on Wednesday. And if you bail out on Wednesday, it'll be twice as difficult to pick it up on Monday. So I'll see you soon. You'll see me Wednesday. I'll see you Monday. Have a good week. And for those of you staying for organic chemistry, this should be really easy. This is Russ Briggs signing off from my bunker deep in the hearts of ESF, protected from all the threats against any worries about exams. Have a good week.